Hello, my name is Will Tobin. I'm going to talk to you about my research project for computer network security, where I basically studied how changes in an underlying system can affect an attacker's ability to use machine learning to find vulnerabilities and potentially exploit that system. So to start off, we started off using differential equations um, as a model for our underlying system. Uh, this is important because it makes sense as inputs to a system change even slightly. Outputs to a system can change dramatically or slightly. And so it makes sense to kind of use differential equations and look at them and try to understand how they relate to the model of a system. So we use differential equations, and I'll start off talking about the data that we got for our first order linear equations. As you can see, the first bar in our results, um, we got simple solutions. They were all exponential. One of those is a negative exponent, one of them is a positive exponent. And we can see that with a very simple neural network with only 3 hidden layers of 16, 24, and 16 nodes each, we were able to get, if you look at the graph, you can see that it's very close. But we were able to get very good, very low mean squared error of 25 and 70, which is a semi-large number, but for the range of that function in that domain, that's actually not a terrible number at all for our model. I'm going to skip ahead to the bottom row that you'll see in results, and that is for our nonlinear first order. We had very low mean squared error for that, and we also had a very large neural network for that. You can read an analysis. I don't exactly have time to explain how I set up that neural network, but it's a very large network, and we can see that the solution to that equation is actually just a second-degree polynomial that we were able to model with very high accuracy. Now, what's more interesting, and this is going to make the point in the end, is the second order linear differential equation solutions for both the real and imaginary roots had very high mean squared error. Um, and it's important to talk about why that is, which is basically the conclusion of this. So to conclude, in talking about basically what our results were, is I found that in this study, for the scope of it, there was no real relation in the linearity or the order of how that changed um, the complexity of the function and how hard it is for a machine learning model to learn it. What I did show, though, was that based on the solutions that we have and the functions that we got, we can see that as the functions change, as the solutions to the equations change, it does get more difficult um, to accurately model this. And that's very important because that basically shows, and if you look at the equations, for example, a second order linear, those have complicated derivatives that, you know, get very large, get very volatile, and we can see that as small inputs to that function change, so does the output in a dramatic way, and it gets harder to model. And so it starts to become apparent that as you have more complicated models underneath, it becomes harder for a machine learning algorithm to learn it. I'm out of time. I hope that sums it up pretty well. Thank you.